jump straight to code.
Where's Jesper?
All right. So I was in the process of creating my first joint, and we still needed a joint axis. It's a frame vector. It's a new frame vector expressed in before joint frame. So it's also going to be fixed in the frame before the joint. This joint axis. Oops. And let's just do 1.0. So we're going to be rotating about the x-axis in before joint frame, which is frame A. All right. So now we have a joint. So let's system that out. That.
Rotate off the x-axis before joint frame.
Joint 1. Let's see what that gives us. And let's not do this thing. All right, so it's just a revolute joint 1. That's the information we get. Let's look at a couple of the classes involved. So we have a class rigid body, and a rigid body has some inertia, which for this first rigid body, since it's the root body, sort of the inertial body, it's null. Body fixed frame, so that was frame A for this first rigid body that we created. A parent joint, which is null for the first body. Center of mass offset. Okay, and then children joints. So a rigid body knows both what its parent joint is and what its children joints are. And then this is just some efficiency thing, and then the name. Okay, so that's fairly simple. Now a revolute joint is a 1 DOF joint, and it has a frame vector called the joint axis. So that's one of the things we had to pass in. 1 DOF joint extends abstract inverse dynamics joint, and that has a whole bunch of things in it, including joint angles, joint velocities, torques, and all that stuff. But we'll see more about that later. And then if you go all the way up the chain, in the end it implements this interface called inverse dynamics joint. And let me just bring up the Control Z. That is strange. Okay, FN. Yes. Here they go. So inverse dynamics joint. So this is the whole hierarchy. There's abstract inverse dynamics joint, and then below that it's 1 DOF joint. Planar joint, which I didn't show yet, but that's another type of joint that has a fixed motion subspace. 6 DOF joint, and a spherical joint. So that's all the examples I covered before. Right? So what can we do with this joint? Now that we have it, let's see, twist stuff. Okay. Well, for one thing we can do is set its joint position. Set Q. Let's set it to 1 radian. And then we can do joints 1 dot update frames recursively. So after you've set the joint angle, it still needs to update the whole kinematic tree, basically, going from frame A to this new frame that we've just created, which is the frame after joint. And then we can do joint 1 dot get frame after joints, which is automatically generated by creating this joint. Dot get transform to desired frame. Joint 1 dot get frame before joint. So that's just going to be frame, what is it, frame A. And this whole thing, where is the home key? It's probably like, let's call this just transform. Transform from, transform. So that's the transform from the frame after joints to the frame before joints. And then just let's scissor out that transform. Okay, so this is the result. So the x-axis in this rotation matrix is just 1, 0, 0, which means that it's constant. Since we're rotating about the x-axis, that's what should happen. And this is just basically one of those basic rotation matrices where it's just a rotation about a single axis. So this is like a sine, cosine, negative sine, cosine, or something like that. And no translation. So just by creating these joints and setting the joint angles, which would normally be coming from sensors, and updating the frames, we can just compute this transform. All right.
How much does the round off error in those affect the calculations?
For any real robot that you would use, I think it doesn't matter. Again, like Nick noted in the first part, probably just errors in joint angle measurements are worse, but really you can't do anything about that. If you just have shitty sensors, then that's it.
Yeah, and typically when we do like unit tests and stuff, we use epsilons of 1e negative 7 is usually a good one, so 7 digits out.
Yep.
And that's usually what you get for when you do all the multiplies and all that stuff. That shouldn't matter.
All right, so that's configuration. That's the first part. And now we can also do joint 1 dot set q dot. Let's set it to 3, and then we can get joint twist. Sorry, it's back joint twist. Twist it back, so we have to back in a twist or passing a twist, and it automatically sets all the frames, so you don't have to match those. You can just do a new twist. And joint 1, or sorry, system without. Twist. Let's try that. So that's the twist of joint 1. So that's the frame after joint that it created upon creating the joint itself. With respect to frame A, which was the frame before joint, and it's expressed in body frame, so frame after joint. And we see that indeed the angular part is 3 radians per second about the x-axis. All right. And then, of course, this is just a twist, so we can just like change frame into a different frame or whatever we want. Okay, that's all I showed so far, I think. All right, so now let's do some more fun stuff with joints. All right. So we had this thing. Let's create this mechanism again. So we have A as our root body, B, C, and let's even do a D. Sure. all of these joints can be just generic types of joints, doesn't really matter. Anything from Revolut to 60LF. So we had our motion subspace thing, where it's like T of B with respect to A expressed in B equals, equals X V times V. Now let's do it right. V A. Okay. So that's nice. So that's a twist of B with respect to A. Let's write this down a little bit more generally, because really what we're saying is that the twist of the successor with respect to the predecessor expressed in successor frame can be written as some linear function of a joint velocity across that joint. So let's introduce this notation. Let's let lambda of I is the parent parent frame, or parent, no, I should say the parent body, basically. Parent body. So let's just identify I with the frame. So let's say that frame B is the same as rigid body frame, rigid body B. Then lambda of B is A, and lambda of C is B. So really what we're saying more generally is T lambda of I with respect to I expressed in lambda of I's frame is X I V and then this is I lambda of I. Okay. So cool. Now suppose we want to know the twist across two joints. So we want to know T, oops, or maybe let's do all the way to the end. So T of D with respect to A expressed in frame D. What is that? Well, what we can do is take the twist of, let's leave a little bit more room. So we probably know the twists locally. So we have T B with respect to A expressed in frame B. But then we know we want it in frame D. So we're going to add everything up in frame D. So we'll have to pre-multiply this join matrix, change frames, H2D from B, plus, what is the next one?
You switched to lambda I and I terminology.
Did I?
I think, yeah, it's
Because
Yeah, I did. Sorry, you're right. That's stupid. Okay, well, this is right, and this was wrong. Sorry. I'll get back to that later. So this is what counts. All right. Plus, what's the next one? So we're gonna have twist across these two joints, or sorry, between these two rigid bodies across this joint. So we'll probably know it locally because we know the joint velocity from our measurement. So we know T of C with respect to B, expressed in frame C. And we just do the same trick of transforming it to that frame D that we want everything to be in. Joint H, D, C. And so you can see sort of the idea of how this works. You just take the local joint twist that you know in body frame and change frame it to a common frame. For example, frame D in this case. So really you can write this as the sum from I equals A to D. It's kind of stupid, but alright. A joint H, well, we want to go to D, and then it's going to be expressed in frame, let's see, wait, there's 3 joints, so I should start at B. From frame I, twist of I with respect to lambda of I, expressed in I's frame. So that's basically what this whole summation is, right? We're just taking the local twist, the joint twist, and transforming it to D's frame, and then adding all of those twists together. So what is this T thing? How can we compute it based on the velocity vector that we know from our sensors? So how can I write down an equation for this twist where this velocity vector directly appears, or the velocity vector for each of the joints? So let's write down a formula for this.
So in summation, you replace the twist with velocity.
Yeah. So now I'm going to write it down properly. I with respect to lambda of I equals x I lambda of I expressed in frame I times v I lambda of I. So let's put that in there. Equals sum I equals b to d. So let's just do sum over all of the joints, basically, if you have some kind of indexing. A joint H I to D X I with respect to lambda of I times V lambda of I. And so that's nice. So at least what this equation shows is that the twist all the way from A to D is just a linear combination of all of the joint velocities, all of the joint velocity vectors, right? Because we're just taking this joint velocity vector, pre-multiplying these two matrices, and then summing up the results. So it has to be linear in these joint velocities. So let's introduce a new vector. Let's just concatenate all of these individual joint velocity vectors and write v from D to A is basically just V A B V B C C D. So it's all of these 3 joint velocities, one after the other, concatenated. So let's try to rewrite this equation in terms of this whole velocity vector. Alright, what needs to come here?
Yeah, joint of H
So that's one block in this matrix. Then the next block is just going to be a joint. I should have made more space. A joint H C to D X C B A. And then you sort of see the pattern, right? So I won't write down the last one. So this, what is the size of this matrix? First, what is the number of rows?
You got something wrong with that X. You got A, B, and C in it.
Yeah, right. It should be in C's frame. Yeah. How many rows? So this is a 6 by 1 vector because it's just a twist.
Six.
6, right? By some number, where the number is, yeah,
Number of velocity.
yeah. So really, yeah, let's call it n, where n is the sum of the ends of all of the joints. Basically, where the sum.
Is it K there at some point?
Yeah, let's actually, yes, let's call it k. Yeah. Sure, k.
Oh well, K was each individual.
Yeah, you could even do something like
Okay, big
k d to a or something like that. So, but basically, it's just the sum of all of the velocity degrees of freedom of all of these joint velocity vectors. So if you have three revolute joints, then it's 3. If you have a 6 degree of freedom joint followed by 2 velocity joints, 2 revolute joints, then it's 8, and so on. Alright, so this is a 6 by k matrix that basically takes in, it's a linear operator that takes in this concatenated velocity vector and returns a twist. So what do you think that kind of vector, kind of matrix is? What is a name for that kind of matrix? So it takes joint velocities and turns it into a twist.
9.
Hey, so this is a Jacobian.
It's not too late to drop the class, Peter.
Was
It's never too late to drop the class.
And so it's a special type of Jacobian that's sometimes called the geometric Jacobian, or a basic Jacobian. That's what Kusama Khatib calls it, and Louis Sentis will also call it that. So that's the mapping from this joint velocity vector across several joints to to a twist, to the twist across all of those joints. All right. And so this is an algorithm, really. So either this summation, or yeah, this basically each term in this summation, this part is another couple of rows or a single row in this Jacobian. So in order to just compute this whole Jacobian, numerically, all we need is the adjoint of these transform matrices and the motion subspace for each of the joints. So the motion subspace in body frame is just constant usually, and these transforms you already calculate normally when you're doing your kinematics. So if you just want to know where your finger is with respect to your foot, then you already need that. So that's sort of for free. And in our code, with the whole reference frame structure, we basically, that's the first thing we do. Once we've set all of the joint angles in the joints that we've measured, we call update frames, and then all of those transforms, all those local transforms, but even the ones to world will be calculated. Or well, lazily, the ones to world, but yeah. So that's nice that we have this Jacobian, because what other people sometimes do is they create this mechanism. They do it in Mathematica, basically. They write down all these transforms, the h's, in terms of the joint angles. For example, all of those basic rotation matrices, they really write them down in Mathematica code. Then they concatenate them all together, and then they just use the derivative function in Mathematica or in Maple, whatever. And then they just let it go for like a day and wait for an answer in terms of all of the joint angles. But really, you don't need to do that, because you already have all of the information that you need from the motion subspaces and the kinematic tree. So this is a much easier way to calculate those Jacobians, those types of Jacobians. All right, so let's do that in code. All right. So in order to do a Jacobian, let's at least have two joints, otherwise it's kind of trivial. So we already had this one joint. We didn't really attach any rigid body to it. So rigid body, create a new rigid body. Let's just call it body 2. Is new rigid body. And then let's not take the first constructor, because that would just create another root rigid body, like an inertial rigid body. Let's take the second constructor, call it body 2. Takes an inertia, so we'll have to create that. And then the parent joint is going to be joint 1. So just tell it what its parent is. And then the inertia is a rigid body inertia. And that contains both the sort of the linear inertia and the angular inertia. So both the mass, well, all of the mass, the center of mass offset, and also the mass moment of inertia. Let's just create one. Rigid body inertia. Which one would be simplest? Yeah, let's just do this one. So there are constructors for passing all of that stuff in. Let's just take the 0 argument one, or the 2 argument one. Inertia 2, and then the root body frame would be joint 1 dot get frame after joint. Just keep it simple. What is up here? Type mismatch. Oh, excuse me. Just trying to make a rigid body and use it as a rigid body inertia. Rigid body inertia. Yeah, let's just do this one. So frame, joint 1, after joint. So this is these 3 numbers are the mass moment of inertia, and then the mass. All right. So now we have our body 2 that's attached to joint 1, and it knows that it's attached because we've just passed in the joint 1 as its parent joint. Then let's create another joint. Revolute joint. Joint 2 is new revolute joint. Oh. Predecessor is going to be body 2. So this is the thing where you say the knee joint is attached to the pelvis joint or whatever. That doesn't make sense. Good. Before joint frame.
Don't let him design a robot.
Body 2. Let's just use the body fixed frame here.
So
joint axis. Let's create a new joint axis just for fun.
So you're kind of being lazy and having the joints just be all on top of each other,
Yeah,
just so you don't have to make a ton of frames.
yeah. And there, I'll show you in a minute a less trivial example. Is new frame vector expressed in body 2 dot body fixed frame 0, 1, 0. Okay. And then let's set this joint angle. Joint 2 dot set Q. Set that to 3. Don't forget to update the frames. So really what we should do is just joint 1 dot update frames recursively. So that basically goes down the tree of joints and updates all of the reference frames accordingly. And you need to do that every time you change joint angles. Alright, so let's create a Jacobian now. Geometric. Actually, one more thing I need to do is add another rigid body. Rigid body, body 3, is new rigid body. Body 3, and I used the wrong constructor, so let's just reuse the inertia, and then joint 2. Okay, so now we have an actual chain. And let's do
create the bodies after the joints.
Yeah. So you start with a root rigid body, which is like the inertial rigid body. Then you attach a joint to that. Then you attach a rigid body to the joint. Then you attach joints to that rigid body, and so on. So it's a little different from SES, where you attach joints to joints, which didn't make. Well, I thought this was more logical. All right. So geometric Jacobian. So it's new geometric Jacobian. And a really convenient one is this, where you just pass in, let's see, what did I call the first rigid body? Do you guys remember? Of predecessor. So predecessor is the first body in the chain, and the descendant will be body 3, and then let's express it in body 3 dot get body fixed frame. That's all you need to do to create. This gives it enough information to create that Jacobian. So, as opposed to putting it all in Mathematica, letting it run for a day and copying all the code, this is all you need, really, as long as you know the structure of your mechanism. And then let's call it Jacobian dot compute. So that actually does that algorithm where it computes all of the terms in that summation and uses them as vectors in the or columns in the Jacobian matrix. And then system.out that print Jacobian.
Typically, you'd only set up the Jacobian once, and every tick you're only calling Jacobian or compute.
Yeah, exactly. Yeah. So let's see. All right, so since this is such a simple mechanism, you can sort of verify it yourself. We had a rotation about the x-axis first, so that's why there's this one here, and then a rotation about the y-axis. Where's that? 0, 1, 0 after that. And since the axes intersect, it really doesn't matter what the joint angles are. So this is a really trivial one, but now let's do a more complicated one. And there's this stuff, nice thing that I use often for tests. Random, what was it called?
Can you go over the format, the rows and columns on that?
The rows and
So
columns.
the first column on your Jacobian?
First column is multiplied against the first joint velocity.
Yeah, so
Second column is multiplied against the second.
Joint velocity.
So angle to velocity.
Since we had
Yeah.
rotation
And you just
on
have
X.
rotations and no translations.
Yeah, in
Yeah.
the first
Okay.
part of the place. That's
And
why I have
they're
X and Y.
collinear
Yep.
axes too, I think, so there's no velocities.
Mhm.
And yeah,
Like not collinear, but the origin is.
what was that, Jerry?
They're on top of, so all you're doing
Yeah.
is two rotations on top of each other, and you're looking at what's the velocity of the point at the, what's the velocity of the origin, there's no velocity, but it is rotating.
But they're both rotating in the same plane,
What's it called?
no, one's
It-
X, one's
like
Y.
a
rotating
U-joint.
this, one's rotating this
Yep.
axis, one's rotating
Yeah.
this axis, so it's kind of going for that.
Yeah, it's like a U-joint.
It's going to the point between them, so it's counted for that.
Alright, so for tests, I often use this class random floating chain. Random floating chain is new random floating chain. So all I have to pass in is a random, which I already have, and then a whole bunch of joint axes. So let's do control 1. So this is just an array of joint axes. Vector 3D. Oops. Um, 3D array. Let's just do this, X, Y, Z, X, Y, Y, Z. Let's go straight use vectors. Oh. Oops. Control 1. Okay, with constant, sure. Let's first just create all the constants. Okay, go up. And actually make the vectors.
So you just created a random robot,
A random robot that starts with a 6-degree
ar-
freedom joint.
arbitrary robot.
Yeah, and then a whole bunch of revolute joints with all kinds of translations and stuff between them and rotations between them.
But not fixed translations. So
Sorry?
fixed link lengths.
No.
All
also-
revolute joints, or
also
no?
varying link lengths and whatever. I just
Well,
use
they're
random.
random link lengths, but once they're chosen, they're fixed.
Sure.
Right.
Yeah.
There's no linear joints, they're all
Yeah,
rotations.
so it's all revolute joints.
That's a good part for a genetic algorithm.
Okay. All right. So then there's another thing called screw tools, which I also use a lot in tests.
Drivers.
Dot set. What was it again? I hate this.
You hate.
Oh no no, I moved that to here. Sorry.
Eclipse.
Random floating chain. Dot set random positions and velocities. All right. And then let's update the kinematics. Random floating chain. Dot. I think we have just get elevator. Yeah, you'll see this often in the code. I consider the root body of the mechanism to be an elevator because that is easy for inverse dynamics algorithms. So if you just consider the robots to be standing in an elevator that's accelerating upwards at 9.8 meters per second squared, that's the same thing as you sort of get gravity compensation or calculation for free in an inverse dynamics algorithm. that's why. Dot get elevator dot update frames recursively. Then let's create a geometric Jacobian. Jacobian is new geometric Jacobian. Alright, so we need a different constructor. This one again. So the ancestor, let's just start at the root of this chain. So that's again random floating chain get elevator, and then there's random floating chain dot get leaf body. So that's all the way at the end of the tree. And then let's just say, for example, in world frame. Okay, that's our Jacobian. We calculate it again. I shouldn't be able to do this. Yeah. 2. Jacobian 2 dot compute. And then Alright. So now we have a new Jacobian that goes all the way from the world to the rigid body after test joint 6. So it automatically created these 6 joints with these joint axes. And we have this 6 by 13 matrix, which is the Jacobian, because it's 6 degrees of freedom for the floating joints plus 7 joints, 7 revolute joints. Yeah. So and this, if you just have the joint velocity vector, so that would be a 13 degree of freedom vector, and you pre-multiply this thing, then you get the twist of this leaf body with respect to the world. So that's cool. And Jacobians are nice because suppose you want to have a certain motion of the end effector. So you know what T, D, A, D is, and you want to know what the joint velocity should be to achieve that. Then you can just do V. What is it? A to D equals the inverse of this Jacobian. A, D, inverse times T, D.
It's not a true inverse since it's not square.
Yeah. So if this is 6 by 6, otherwise you can do like a pseudo inverse, and you'll get the least norm solution, like the smallest norm thing. So yeah, let's write a plus. And another issue is that even if it is 6 by 6, this matrix, then you could still be in a singularity, where, for example, for your leg, if you have a robot that has a leg with 6 degrees of freedom, and your knee is stretched, then you can't achieve a velocity in this direction instantaneously. You'd first have to bend your knee a little bit so that you get out of this singularity, so that you can actually achieve the twist of the foot with respect to the pelvis that you want, for example. Yeah, and a singularity shows up as really a singular matrix. So if the inverse of this Jacobian doesn't exist for a 6 degree of freedom mechanism, then you're in a singularity. Yeah.
So it's 13 because 6 for the elevator, 7 for the joints.
6 for the floating joint between the elevator and the first floating rigid body. And then after that first rigid body, there's 7 more joints. Yeah. All right. Okay. Who did I use? Did I do anything? Okay. Yeah, this is another nice one. You don't actually have to compute Jacobians to calculate the twist all the way from the start of the chain to the end. It can, if you just want to know what that twist is, and you don't actually have to invert the matrix to find joint velocities or anything, then you can use a twist calculator. Twist calculator. And a twist calculator requires just two things: the inertial frame, so let's make that world, and the body, which is going to be random floating chain dot get elevator. Alright. So and then we just call it twist calculator dot compute. And then we can ask twist calculator for the twist of any rigid body in the chain. So let's do, for example, random floating chain. Just this again, random floating chain dot get leaf body. Sorry, twist attack. Sorry, twist. Leaf body. Twists. And then sys out that again. So now we have the twist all the way from the start of the chain to the end. And internally, this is really simple, this twist calculator. It's basically just doing that summation that I showed before. So the compute method basically just computes the successor twist for all the joints. So it takes the predecessor, successor, and it backs the twist across the joint. So from the predecessor to the successor, and then it changes frames to successor frame and adds the previous twist, basically. So you're just adding twists successively. And really what this twist calculator ended up being, and that wasn't the idea originally, but it's sort of the equivalent of the reference frame tree that we have for the kinematics. So as long as you have a twist calculator that's up to date, so you have to update this every tick again, then you know the twist of any rigid body with respect to the base. And you can also, this is a recent addition, calculate relative twists. So twist, relative twists, twist calculator dot back relative twists, and then let's just pick two bodies in this chain. Let's make the base be random floating chain dot get revolute joints dot get 2. So this is going to be the second joint in the chain, or the second revolute joint at least.
You started 0 or 1?
It's 0 index.
Zero indexed. It's Java. So the third one. Dot get predecessor. So the predecessor of that thing, and then go all the way to the end. So let's do a random floating chain. Dot get leaf body again. And format that so we can read it. And then sys out relative twists. So this is the twist of test body 6 COM with respect to test body 1 COM expressed in test body 6 COM.
So does it do the same way as reference frames, where they both go to the origin
Yep.
and then come back up?
Yeah, yeah. So since you know the after the twist calculator.compute call is done, you know, what is it? It was 1 and 6. Okay, so let's call it T in world frame. Or I think it calculates them in body frame. So T in 6 of 6 with respect to 0, and it knows T of 1 with respect to 0 expressed in 1. So by just manipulating the frames in which they are expressed and then subtracting them, you can compute the relative twist. Yeah. Okay, so that's really nice. I could also show you that taking a Jacobian and multiplying it by the joint velocity vector results in the same twist as using the twist calculator. So you can figure that out by yourself, I guess. All right, so that's it for Jacobians for now. Then one more topic, which is wrenches.
Is that on today's agenda?
Screws now can do wrenches.
A British person can do this. It's called spanners.
All right.
I'll be screwed.
So velocities are one important thing in mechanics, and the other, well, another important thing is wrenches. So forces really, and actually wrenches are sort of easier to understand, I think, than twists initially, because with twists you have that weird thing where you have to imagine a rod attached to the moving body and then going through the origin of the frame in which it's expressed or whatever, and it's difficult. But for wrenches it's quite easy actually. So imagine a rigid body with a reference frame. Let's call it I. And imagine that there's a point here called R1. And there's a force F1 exerted at that point. And then there's another R2. And F2. And so on. So you can add as many forces as you want. The wrench expressed in frame I on body I. So this is expressed in. And this is exerted on. And with Jerry we had some discussions about this notation. It might not be as nice as we'd want it to be, but this is what's used in Dijndam's book at least. It is defined as, so it's going to be angular and linear again, just like with twists. The linear part is just the sum of all forces, sum of Fj, so sum over all j's, where here in this example j is just 1 or 2. And then for the torque part, so the angular part of the wrench, it's sum j rj cross fj. So this r can just be seen as moment arm that you just take the cross product to compute the torque caused by this force, and then add the torque caused by this force. So really this is a torque, and this is a force, and or angular part and linear part. So yeah, that made a lot more sense to me initially than twists. Yeah, already intuitively. But the nice thing is, that you can, they sort of cooperate well with twists. So if you have the twist of this body with respect to some other frame, say frame J here, and you know the twist of I with respect to J expressed in I's frame, and that's omega I J I V I J I. Then the way in which they sort of cooperate is that if you take the dot product of this twist and this wrench, then you get the instantaneous power. So really this torque is sort of what's called collocated with this this angular velocity. So they're sort of expressed in the same coordinates, and their dot product makes sense and means sort of power caused by this torque. And then you just add the power caused by the force, which is just velocity. And so this is just the velocity of the origin if it's expressed in body frame, right? So in body frame it all makes sense. So we have W I, well, let's just first do the dot product, dot T I J, I is
These J's are the different J's than the sum and in the sum.
Yeah, maybe I should have, but alright, I think it's clear. Yeah, so this is the power associated with this twist and this wrench, really. So, and the dot product, of course, can just be written as transpose the first one times the second one equals T I J I times ds equals still the same P. Alright, so that's nice. Now we had a couple of nice properties of twists, like you could do the addition and all that kind of stuff. So addition sort of works the same for wrenches. If you have two wrenches exerted on a body that are expressed in the same frame, so they need to be both exerted on the same body and expressed in the same frame, then you can add them up, and it's just the net wrench has some meaning, of course. You can also add up wrenches exerted on different parts of the mechanism, and then it's sort of the wrench exerted on the mechanism as a whole. So that makes sense. For example, if you have a robot that's standing on the ground, so there are wrenches exerted on both of the feet, you can actually sum up all of the wrenches, even if they're exerted on different bodies, as long as they're in the same frame. And then the result, the total external wrench on a body is actually the same as the rate of change of momentum of the robot as a whole, even though there might be joints and there might be joint torques. But we'll sort of get to that later. Alright, so that's one property. Then
I think the thing I didn't like, if I remember right, with wrenches is that there should be that third frame.
yeah, just like with twists.
Because it should be the frame that you're reacting from. So this, where the twist has the base frame,
Yeah,
the wrench should have a base frame. So it's where your virtual actuator will be connected if it's produced in this wrench.
yeah.
That's,
It might be interesting to pursue that notation,
Yeah.
see if it helps or
yeah.
it's just
But-
really verbose.
I mean, so I think by not having an NW, you're always implying that the forces are being exerted from the world.
Yeah, but also not
What does
really.
it matter if you're a body? You don't.
Because you can also talk about the wrench exerted across a joint, and then it's really from one body in the chain to the next.
You need to know
So-
the direction.
yeah.
Is summing those two in opposite directions will cancel each other out.
So I think in hindsight, it would maybe be nice in code to have that third frame, yeah. And I might actually do that the next time I implement this in a new language or whatever.
Refactor spree.
What do you mean?
Let's go.
What do you mean?
Like C?
I don't know.
C++.
Maybe.
Come on.
Smell that?
New
Yeah.
world.
Scratch.
Scratch.
Lisp.
All right, so, but another property that we had for twists was that we could change their frame, right? We have this rule, T. So let's just take this this one, for example, express it in a different frame. TK equals a joint H 2K from what was expressed in I, T I, J I. So that's how you get this T. Let me actually do it the other way around, maybe. No, this is fine. This is fine. Okay, so TKJI is this. It would be nice if we had a similar rule for transforming wrenches to a different frame. And the way we derive this rule is by noting that power must be the same in no matter what frame the twist and the wrench are expressed in, as long as they're expressed in the same frame. So you can do that one dot the other, and it makes sense. It should always be the same number. So we have, as a second equation, W, K, comma, I, transpose, T, what is it? K, J, I, equals P. So let's put this in here. So we have W, K, I, transpose times a joint H, K, I, T, I, J, I equals P. And then so that basically shows, since this is P and this is also P and these two things are the same, we have that W I transpose equals W K I transpose times a joint H K I. All right, and then let's take the transpose of all of this and write W I is, so if we take the transpose, this comes first, a joint H K I. I mix up the order in which I say these, it's funny. Transpose, so the transpose of this adjoint matrix times W K I. So that's our transformation rule for wrenches. And so what does this mean? Let's see. Erase this. So we had the adjoint of H K I. That is just sorry, not over there. R K I P hat K I R K I. So the transpose of that thing so that'll sort of invert this rotation matrix IK. This will be, so just as a side note, V hat K I R K I transpose equals R I K V hat K I transpose. And so this is a skew symmetric matrix. So taking the transpose of a skew symmetric matrix does what? What is the property that defines a skew symmetric matrix? S equals negative S transpose, or S transpose equals negative S. So that's the same as R I K, negative R I K V hat K I. So that's the term that comes here. Zero goes over here, and another R K I. So what happens if you post multiply a wrench? So a wrench is so W equals, let's just do tau and F, so the torque part and the force part. If you post multiply a wrench, then the force part is just rotated. So whereas previously with the twist, the part that was just rotated was the angular part, here it's the force part that's just rotated. And with the torque, you rotate the previous torque, like the torque of the wrench as it was expressed in the frame initially. And then you muck around with it. You basically add this cross term based on the translation between the frames. Yeah.
H1, did you do something? Because you got IK different on all the R.
So RIK and RKI, you mean?
No, the bottom right
Should all three of those be the
RKI
same?
Oh,
should
right.
be doing this.
Yeah. And so one thing to note, I'll let you derive it yourself, but it's kind of funny. A joint HKI transpose is the same thing as a joint HKI transpose. But note that this transpose isn't the same as the inverse. So you can't just take the inverse of, you can't just take HIK and do this joint thing. You have to actually take the transpose. So that actually also has sort of a meaning. This comes in handy when you're actually trying to implement all of this in an efficient way. All right, so that's wrenches. So now we have, just in a couple of minutes, based on our knowledge of twists, we have all of the necessary rules for manipulating wrenches. Then one more nice thing. Okay, let's keep this rule. Yeah. Okay. So previously we were talking about Jacobians for velocities, for twists. And we had something like this. T, let's call it, let's just do that example again, of D with respect to A expressed in frame D is, and let's introduce this notation also, a Jacobian with the same indices, D, A, D, times V from A to D. So that was just the Jacobian that I derived previously. So suppose we have this twist, and we have a wrench that's exerted on D. Then the power exerted by this, the power associated with this couple of a wrench and a velocity and a twist is P equals W D D transpose times D D D. And then let's fill that, let's substitute this in. So that's W D D transpose J D A D D A D. So that's one equation for power. Now another way to calculate the power, how do you say that? Not exerted by, but in a mechanism, basically the power that the actuators in a mechanism deliver is you have a joint torque vector that's co-located with these joint velocities. So for each of the joints you have a tau. So for example, tau A to B, tau B to C. And you can do the same thing as with the velocities and put them all in one vector. So you can take all of this and turn it into tau from A to D. And the mechanical power should be tau A to D transpose times V A to D. Right? You take a torque, you multiply it by its associated velocity, and you sum all of that up, and that's the power exerted by all of the actuators. Equals P. So now we have a second equation for the power. So equals tau A to D transpose V A to D. And this needs to hold for all possible velocities. So we can just get rid of this on both sides of the equation. So we have W D D transpose J D A D equals tau A D transpose. And let's take the transpose of this whole equation. So again, these switch signs, or switch places. G, D, A, D. Transpose W, D, D equals tau A, D. So this is basically your J transpose F equals tau. It's sort of a very well-known standard equation in robotics. That's where it comes from. So just power equivalence, whether you talk about twists and wrenches or joint velocities and torques, results in this equation. So basically, if you want to exert a certain wrench with your end effector, then this equation gives you the torques that you need to exert in all of your actuators to achieve that wrench. Yeah. All right, so let's do one more thing in code, and then we'll be done today. Want to switch over to here?
Yeah. I'm just looking at the notation for W and stuff. you put the third letter in it, and it all just makes sense, and you don't even need them to be.
Yeah.
Probably talk more about that later.
Alright, so we open Jacobian, so that's nice. Let's see what the methods are on that Jacobian. Or let's just use that Jacobian 2 thing. So there is, hey, that's convenient, there's a compute joint torques for a given wrench. Control 1. Take a wrench, new wrench. So that's supposed to be the wrench exerted at the leaf or at the body frame of the Jacobian. So let's do that. So one of the constructors is this one, where you pass in the body frame. So that's going to be Jacobian 2 dot get end effector frame. Jacobian 2 dot get end effector frame. And then force torque. Let's just do a random thing again. Vector 3D. So that's our random wrench. And then this is going to result in a vector or the dense matrix 64F with our matrix library. Torques. And this is probably not going to work right now because of arguments, not or reference frames not matching. Because we had that wrench which was expressed in body frame, and the Jacobian, if we scroll up here and go to how we define this Jacobian, it's oops, Control Shift, it doesn't work anymore, it's very yeah, so it's the third frame, it's expressed in world frame. So let's just, before we do this, just do Jacobian.change frame to Jacobian.get end effector frame, and then we'll have to recompute. And then it's system of this.
Will it be faster to change the wrench frame?
Yeah, it's another possibility. Yeah, so you need to sort of, that's why I didn't build in all of the automatic change frames, because you might end up doing a lot of computation that's not necessary. The nicest thing, I think, would be for it to figure it all out. Just give it a bunch of things it needs to do, and it automatically figures out what frames to express things in optimally. That would be really cool.
What class of problems does that fall in?
I don't know. Alright, so let's sys out this.
NP hard?
Give it to Peter.
Oop, that's not right yet.
He's got masters.
World does not match. Oh, did I did Jacobian. Should have done Jacobian too.
Jacobian.
Jacobian 2 to get an effective.
1109.
We can do Jacobian 2. Right.
Yes. Alright, now there we go.
Mini torques.
Well, not really mini torques, it's just the notation is really stupid right now. Alright, yeah, so calculates 13 torques, where the first 6 are really the wrench across that first 6 degree of freedom joint we created. And The reason that it's a wrench is that we describe the velocity because if we had this motion subspace, which was just identity. So the joint velocity vector was just a twist, and the thing that the force space joint parameter that results in power for a twist is a wrench, right? So it always needs to be the case that wrenches dotted with twists are powers, and joint torques dotted with joint velocities are powers. Otherwise, it doesn't make sense in terms of units and stuff. Yeah, so now we're able to, for any mechanism we want, compute the velocity of the end effector, any point on the end effector with respect to the base, and also calculate torques that achieve a certain wrench at the end effector, basically.
Jacobian is just pseudo inverse.
So you're taking the transpose, and I think what that ends up doing is computing the joint torques that minimize. Yeah, basically you're minimizing the norm of the joint torque vector.
Yeah, I would just make sure that the transpose is for torques and inverse is for velocities.
Yeah. Yeah, because this mechanism is probably redundant. It could have achieved this wrench in a different way. Also, if you have you don't. So since we have a transpose here as opposed to an inverse.
For a linear chain, it's a one-to-one mapping.
Sorry, what?
When you do tau equals J transpose F, there's no. Let's see here. You can get for the same wrench. Given a wrench, there's only going to be one set of torques.
Yeah.
Is that also true if it's that turns between them?
But the other way around. So given a bunch of torques, they can result in different effective wrenches.
Yeah, I guess you can think about it as like in a static situation, all of the bodies should be in static equilibrium while exerting a torque at the end effector. I think that's how Craig describes it. But Jacobians don't just, I mean, they also have uses when joints are actually moving with respect to each other. Yeah.
In that, so what if you apply those torques, everything will behave exactly as if you had applied that wrench instead.
Yeah.
Whether it's dynamic or static.
Exactly. Yeah. And that also means that if you only have a 1 degree of freedom mechanism where it's basically just a pendulum, and you have a wrench that's along the line of, well, basically in any direction other than the rotational torque direction, then you can still achieve that. There's just going to be not any torques associated with it, basically. So if you're trying to pull on the end of the pendulum in that direction, then J transpose F is just going to result in 0 torque because, well, just because of the way your joint constrains motion, you don't have to exert any torques to achieve that or to compensate, to have the same effect as that wrench.
Right, because that wrench would have no effect.
Yeah, exactly. All right, that's it, I guess. Any questions?